So now we're going to take a look at second order reactions overall, and we're going to approach it the same way like we did for the first order overall reactions. So as we saw previously, at the second order reaction, and again, this is the overall order of the reaction. So we can say generally, we can write the rate expression for this, the rate law expression. So rate equals K, and if we just have, it can be the concentration of one of the reactants raised to the second power. Let's say we have a different reactant, let's say B raised to the second power, or we could have the concentration of each of the reactants raised to the first power. Either way, when we add together all of the exponents in each of these, we end up with 2 as the overall rate of the reaction, right? So any of these 3 that I just listed here are second order reactions overall. For simplicity's sake, let's just do the first one for right now. Okay, so we'll use that one as our template. So as we saw, we have rate here being equal to, general rate equation. If we have, let's say, for example, A turning into a product, we can write the rate expression for this. A disappears, so it's negative value delta A over delta T, right, over time. And then if you were to write the rate law, like we saw up here, right, that would be equal to then rate equals K times A squared for a second order reaction overall, and again, second order with respect to A. We can make these equal to each other, just like we did previously. So we can equate these. We can say negative delta concentration of A over delta T equals K concentration of A squared. And then we're going to save you the calculus this time. We can apply calculus to this. Integrate. And go through that process, we end up with the integrated rate law for the second order reaction, and we end up with the following. So we get 1 over the concentration of A at time T equals rate constant K times T plus 1 over the concentration of A at time 0, right? This is the integrated rate law for a second order reaction. Integrated rate law for a second. Right, and again, we're not going to go through the calculus and the math involved. We'll save that for a higher level class. We just need to be able to use this equation here, the integrated rate law expression, to solve for any of these unknowns in equilibrium. And just like the integrated rate law for this first order reaction, when we have our expression written this way, we can approximate it to a straight line, or we can equate it to a straight line, y equals mx plus b. So in this example, our y is 1 over the concentration of A, that's our y value. Our x value is going to be time. And then the slope here is actually equal to the rate constant K. And then the y-intercept would be 1 over the concentration of A at time 0. Right, that's your y-intercept B. So again, making some equalities, making some approximations, we can turn the integrated rate law for a second order reaction. We can approach that graphically. So if you were to plot, for example, the 1 over the concentration of A versus time, and you were able to get a straight line, well, then that tells you that that particular reaction, right, is second order with respect to whatever that reactant actually is. From that straight line, we determine the slope. The slope is equal to the rate constant K. Similarly, like with the first order reaction, we can set, in order to determine the half-life, so T1 half For second order reaction, here we can set the concentration of A at time t being equal to half of concentration of A at time 0, right? So that's what we define the half-life is when the concentration has decreased to half its original value. What we end up with then is 1 over half of concentration of A at time 0 equal K T1/2, so the half-life, plus 1 over A at time 0. We rearrange that equation and solve for T1/2. Okay, I'm not going to go through the derivation here, but we end up with half-life. And you can practice this. You can try this, do the math, go through the math. That'll give you some extra practice with, reviewing manipulations and algebra, etc. T1/2 here, the half-life will be equal to 1 over K times the concentration of A at time 0. So what we actually see is that for a second order reaction, the half-life actually does depend on the initial concentration. For a second order reaction, depends on the initial. And that was not the case for the first order reaction. We saw that the half-life was independent of the concentration. So we've seen first order reactions overall. We saw the integrated rate law. We talked about half-life. We saw second order reactions overall. We saw the integrated rate law and half-life for that as well. We can also run into and encounter what are known as zeroth order reactions. Okay, and if we think about, again, a general reaction where A is turning into products, if it's zero order with respect to A, we can write an expression for this. So the rate there would be equal to K, rate constant, times A to the 0th power, right? So that would mean, and what is any number raised to the power of 0? Well, this here becomes 1. So then our rate is equal to K times 1, which is the same as K. So for zero order reactions, the rate is simply equal to the rate constant, and it's independent of the reactant concentration. Right? You don't see these very often. The most common types of reactions that we'll see are first order, and we'll see second order reactions. So zero order reactions are possible. And again, we can integrate this as well. The integrated rate law here, we have a half-life. In addition to that, we talked about the first and second order means previously. Higher order reactions like third order, etc. Those are very, very, very rare. We're not really going to encounter those in our class.